All right. To those of you who just joined, again, welcome to the second virtual symposium of 2026. My name's Alex, and together with Alex Grenning, we'll be your co-hosts for the 2026 season. And we're really excited because we have a pretty great lineup of speakers for this year, starting with Professor Christian Malapit of Northwestern University and Dr. Kate Harper of AbbVie. But before we dive into those talks, as always, we have a few division announcements to share with you. So first of all, the ACS Spring is coming up pretty quickly. So that's taking place in Atlanta this year, March 22nd to 26th. And the division has a really great lineup of symposia for you. On this slide, you'll see the various awards symposia planned. So if you're attending the conference, we really hope that you can attend the symposia, and we look forward to seeing you. We also have some great joint symposia planned. So likewise, if you're there, please try to stop by. Next, the nominations for the Industrial Investigator Awards, the due date is coming up pretty quickly, so that's February 3rd. And these include the Technical Achievements in Organic Chemistry, which recognizes professional bachelor's and master's level chemists, as well as Industrial Early and Mid-Career Investigator Awards, which recognizes independent investigators. So these are open to industrialists and government sectors, with nominations from underrepresented minorities being especially encouraged. So again, these are due by February 3rd. Next, for those of you who hopefully most of you are aware, but the 16th Graduate Research Symposium is happening at Emory University this year from July 23rd to 26th. And the application/nominations for this are due on March 10th. So the Graduate Research Symposium provides an opportunity for graduate students to interact with leaders from academia, industry, various funding agencies, and publishers all at a single venue. I actually had the opportunity to attend this when I was in my fourth year, and as lame as it is to say, it was pretty life-changing. So if you're eligible, I really encourage you to apply and attend. Next, the 2026 Summer Undergraduate Research Fellowship applications are due on February 17th. So this recognizes outstanding undergraduate students in organic chemistry attending college and university in the United States. So again, if you're eligible, please apply. If you're interested in the pharmaceutical industry as a career path, the ACS Future Pharma Innovators Program might be for you. So this program provides an industry mentor and a stipend to travel to the fall ACS meeting to present your research and network with other program members and industrial chemists. So applications for this are due on March 6th. And again, we really encourage you to apply. And lastly, just a quick announcement about a webinar taking place on February 10th on skeletal editing. So this was jointly organized by the Division of Medicinal Chemistry and the DOC, and it'll feature speakers like Professor Mark Levin and industrialists from Merck and PharmaBlock. So you do need to register for this. However, attendance is free. So please register on the ACS Medi webinar. And on that note, I think we're ready to dive right into our talks. So I'll turn it over to Alex so he can introduce Christian.
Thanks, Alex. It is a pleasure to co-host the virtual symposium with you. And I want to quickly thank Steve and Scott for all of their previous help with this and mentorship. Christian, can we get you to pull your slides up at this point while I introduce you? Alex, you might need to stop sharing. There we go. Okay, so our first speaker today is Professor Christian Malapit. He's at Northwestern University. He is from the Philippines originally, and he received his Bachelor of Science and Master's of Science degrees from Manila University. In 2016, he received his PhD from the University of Connecticut, working under the mentorship of Professor Amy Howell, Of course, we all know her as our fearless leader of the Division of Organic Chemistry quite recently, and also advisor to many PhD students, including Christian. During that time, he was also the Boehringer Ingelheim PhD fellow. And during this time, I actually met Christian at a GRC conference, and he shared some really beautiful chemistry that he was working on, transnitrylation chemistry. It has stuck with me to this date. Following his PhD, he did a postdoctoral stint at University of Michigan, working with Professor Melanie Sanford. And following that position, he moved to Northwestern University, just across the lake, right outside of Chicago, Illinois, in 2022, where he began his independent career. Before I turn the floor over, let me just make a few other comments about Christian. In addition to his fellowship with Boehringer Ingelheim, he has received some beautiful awards, NIH Pathway to Independence Award, and most recently was elected to the Philippine American Academy of Science and Engineering. With that, let me just say welcome to Christian on behalf of the entire audience, and we look forward to hearing what you're talking about.
Awesome. Thank you so much, Alex, for the introduction, and thank you, Alex Grenning and Alex Holonia, for inviting me, and to the team for creating this wonderful event for us. When I was probably 10 years ago, I've been a big fan of this ACSDOC Virtual Symposium, and it's really exciting for me to be able to share something that I've been working on today. So my topic for presentation is the development of electrochemical methods for radical-based reactions. And I'm going to talk about two transformations for today's talk. So our group was established 2.5 years ago, and we started to create at least two distinct research programs. The first one is the topic of today, electrosynthesis. Mainly how we take advantage of our expertise in organic chemistry, transition metal catalysis, and electrochemistry for the development as well as discovery of new reactions. We also have a research program in the development of novel organic compounds as well as electrochemical processes for sustainable strategies in energy storage, electrocatalysis, as well as for degradation of forever chemicals, for instance. So what I'm going to share today are two short stories under our program of electrosynthesis. And in thinking about this, obviously, I'm not the only person who did all of this work. These are actually the people behind what I'm going to share today. This is my research group 1 year after Malapit Lab was established. And this is my group last December when we celebrated the holidays. And I am really thankful for these amazing scientists. Without them and without their hard work, I don't think I'd be here presenting today. So when I was thinking about how I'm going to share some of the work we're doing in the last 3 years, I really wanted to present this in the perspective of a young research group. And I know that there's a lot of grad students and postdocs in the audience. So I really wanted to be able to share a story on how we start with a simple project, take advantage of the lessons that we've learned, and use them to elevate into research programs. So what I'm sharing here is actually a reaction that has nothing to do with the stories I'm going to share today, but this is where it all began. So back in 2019, I was a postdoctoral scholar and I wrote an NIH proposal. And the idea is to use electrochemistry to synthesize aryl fluorides, for instance, from organoboron or aromatic CH bonds. So when I started my career at Northwestern, I was blessed with two amazing postdoctoral scholars who started with me, Dr. Max Bujalel, who is now at Merck, Dr. Eva Alvarez, who is now assistant professor at University of Virginia. So both of them, they've been working on a lot of electrochemical methods in my group. For instance, Max has focused mainly on fluorination of organoboron reagents, and Eva focused mainly on electrochemical CH functionalization, specifically fluorination of aromatic CH bonds. After about 6 to 9 months of putting so much time into these two transformations, I just want to really cut it short. In summary, what happened is that none of these reactions worked. Until today, we could not get these two electrochemical methods to work at all. So that's the first lesson that we had to accept. The second and third lessons are the foundations of the two stories I'm going to share with you today. So what Max found is that if you electrochemically oxidize an aryl boron reagent, it's actually challenging. In fact, there's not a lot of methodologies out there that does this. And so we started to think of the idea that can we use electrochemistry to generate aryl radicals? And from that aryl radical intermediate, we could do several transformations that might be unique with the well-explored transmetallation functionalization reactivity of aryl boron reagents. So there are two fundamental challenges that we have learned as early as possible. First, aryl boronic acids are difficult to oxidize. For example, a phenylboronic acid oxidizes at 2 volts. That's the potential where DCM would also oxidize. But the potassium trifluoroborate salt would usually have a much lower oxidation potential, in many cases about 1 volt less. So we started with aryl BF3K salts, at least in our initial studies. The second fundamental challenge, which I think it's the most problematic for aromatic system, is that once you generate the aryl radical electrochemically, as you can see here, if you do multiple scans in a CV, the current drops, denoting passivation of the electrode. So we started to propose that if you generate the aryl radical, it then grafts into the electrode surface, and thus any productive chemistry that you want will not happen. So we are synthetic chemists, so we started to dig in electrochemical reactions. So we started to oxidize this aryl BF3K salt with a potential of about 1 volt. And if we would generate this aryl radical, a signal of that would be trapping it with a known trapping chemical reagent like triethyl phosphide. So we would easily analyze the reaction by phosphorus NMR. We never get past 5% yield, no matter what we do in our optimization. But we've learned 2 additional fundamental challenges in addition to high oxidation potentials and grafting on the electrode surface. We've learned that homocoupling could happen because one could imagine that if you generate aryl radical electrochemically, you would have high concentration of the aryl radical at the electrode surface, and therefore homocoupling would be a very well-believed reactivity to happen. The second problem could be an over-oxidation, and this leads to decomposition. It could be grafting followed by over-oxidation reactions. Knowing about those at least four fundamental challenges, we started to think of a strategy. So when you do electrochemical reaction, what you usually do is you electrolyze the reaction through time by applying a constant potential or constant current. So if we are going to look at the reaction that we want, so if you oxidize organoboron and indeed you generate the aryl radical, and you are constantly oxidizing at the electrode, this aryl radical will now have a tendency to either graft, homocouple, or undergo over-oxidation near the electrode surface. What we wanted to do is oxidize and lead a diffusion reaction, a diffusion mechanism in order for a chemical step to happen. And so an interesting electrochemical strategy that people have looked at before us, for example, the groups of Baran, Longlu, Modestino, Alistair Lennox, and many others, in the past 5 or 7 years, is to use alternating polarity electrolysis. We believe that alternating polarity electrolysis would mitigate old and unwanted reactions that we are seeing with organoboron chemistry. We started to look at simply with this simple scheme mechanism here. So once you do an oxidation reaction, you would generate this electric double layer, and then you would then oxidize the organoboron reagent. By pulsing the electrode potential, usually in a rapid manner, so you switch the polarity of the electrode, suddenly the electric double layer would also rearrange, allowing some sort of electrostatic repulsion of whatever intermediate you're generating, and allowing diffusion probably to happen rather than grafting or homocoupling. So how do we set up this reaction? It's actually quite simple. So we use an electrosyn, and so normally you would run it at constant current or potential. So the highest yield we would obtain using that under a platinum electrode is 19%. But once we start to apply alternating polarity, and the good thing with alternating polarity is you can actually control how fast you want the polarity switch to happen. So that's given in the value of frequency. So by slowly switching the polarity of the electrode at 0.1 hertz, we now start to see 90% production of the desired product, telling us that the generation of aryl radical using alternating polarity, at least within these frequencies, is highly efficient. As the frequency starts to go so fast, suddenly the yield goes down, and this could be so many different reasons depending on the reaction. I will talk about that later. Another thing that you can see, or at least we can see by naked eye, is that when you apply controlled potential electrolysis, this is how the electrode surface would look like. So you would see a lot of junk being grafted or deposited to the electrode surface after electrolysis. This is what you will see on the platinum surface if you apply alternating polarity. In fact, when we do this pulsing, my students would say that they would end up with a more polished platinum electrode than the platinum electrode that they started. Since we are also a methodology group, so we could actually showcase this organoboron to CP bond formation as a methodology. So you could see that we could tolerate some functionalities. Some are heterocyclic compounds, but I really wanted to highlight aryl chlorides and bromides can be tolerated. And this is interesting to us because this is an oxidative process. So having an aryl chloride that's not being touched in the reaction is great because you could actually couple this with palladium, nickel, copper cross-coupling reactions for further functionalization reactions. We could also trap the aryl radical with selenium, tellurium, as well as sulfur to generate different functionalized aromatics. So as I've alluded earlier, what we wanted to do is use electrochemistry, not only to develop a method, but what we wanted to do really is discover new reactions. And today I'm going to share two of those new reactions that we were working on. So the reaction we really wanted to target is the cross-coupling of an alkyl carboxylic acid and an alkyl boronic acid. As you can see, both of these reagents are quite either abundant, stable reagents, or highly used in organic synthesis. So they have a very rich chemistry. For instance, carboxylic acids have been reported that under basic condition, the carboxylate could undergo anodic oxidation to generate carbon-centered radical. First reported by Michael Faraday about 180 years ago, and then later on worked by Kolbe, and this is now called a Kolbe reaction, wherein this carbon-centered radical either undergoes homocoupling or cross-coupling with another carbon-centered radical. Simultaneously, about 80 years ago, alkyl boronic acids at their boronate states, usually under basic condition, would also undergo oxidation and generate carbon-centered radical. Despite the very rich chemistry of these two alkyl carboxylic acid boronic acid reagents, there's never been any reaction out there, either uses a chemical reagent, a transition metal catalyst, or a photocatalytic reaction that allows us to directly cross-couple alkyl carboxylic acid and boronic acid. So this is, in fact, one of my dream reactions since I was a postdoctoral scholar. So we were hoping that we would be able to use electrochemistry in order to generate two carbon-centered radical and allow heterocoupling to happen. And so Max has been working on this project while he was in the group. And the idea is to start with a Kolbe-derived conditions, right? And usually they would use a hydroxide as the base. So you would deprotonate, quaternarize this reagent. And in most cases, we usually observe zero to trace of the heterocoupling. As you can see, this is actually a very difficult reaction because you would also see homocoupling of the acid, homocoupling of the boronic acid, but also a lot of over-oxidation products, usually over-oxidation of the boronic acid, over-oxidation of the carbon-centered radical that you would generate into their carbocation to become alcohols, aldehydes, and sometimes carboxylic acids. So there's a lot of things going on. If we start to apply pulse electrolysis under these conditions, that's when we start to see trace amount of the desired product, but it's never been the solution. But once we start to do pulse electrolysis, we start to eliminate some of these unwanted oxidized products. Mostly, we just end up with homocoupling of the acid, followed by homocoupling of the organoboron, and then trace amount of the heterocoupling. And the reason why that's the case is because carboxylate is a lot easier to oxidize than the boronate. So if you apply a Colby-type electrolysis, the first thing that would happen is homocoupling of the carboxylate. And once that's consumed, that's when you start to see homocoupling of the organoboron fragment. So knowing that alternating polarity can do something, but not the yield, we've learned that activation is something that's important we need to consider. But the redox potentials of these two activated species don't match. So if you cross-couple just the acid and the boronic acid, this would be no reactivity because their potentials are so high. If you cross-couple a carboxylate and the potassium trifluoroborate salt, you would see some reactivity, but it's going to be mostly homocoupling of the acid because it's a lot easier to oxidize than the organoboron fragment. But then we found that if we activate boronic acid in situ with a controlled amount of TMAF, so based on our mechanistic studies, what's happening here is that TMAF is activating the boronic acid in a somewhat slow release fashion. And we would start to generate mostly a monofluoro bis-hydroxy or a bis-fluoro monohydroxy boronate acids. And based on our CV and NMR studies, we were able to identify these intermediates as the predominant intermediates. And more importantly, their oxidation potentials are matching to that of alkyl carboxylate. So by using this controlled fluoride activation and alternating polarity electrolysis, when I start to see high reactivity and usually up to 60% yield of the desired heterocoupling product. So this was a really exciting day for us when we started to find this reactivity, as well as understanding some of the important mechanism or intricacies of the activation, as well as the interplay with alternating polarity electrolysis. So from here, we were able to develop a very nice substrate scope. Alkyl boronic acids are usually not highly commercially available, but you can easily make them from many methods. In our case, we took advantage of hydroboration that is so selective to generate boronic acids in situ. So usually we just have to swap the solvent, put in the carboxylic acid, TMAF, electrolysis, you will get to the cross-coupled product resulting from the cross-coupling of alkyl boronic acid and alkyl carboxylic acids. With respect to the functional group tolerance, we could tolerate aryl chlorides in most cases. We could also tolerate some of the arenes that are usually difficult to tolerate because they would be prone from over-oxidation if alternating polarity was not employed. For those of you who are interested with mechanistic studies, I'm not going to focus on this talk due to the limited time, but we do have a recent publication in JAX 3 months ago, where my postdoc Jake actually drive this project. So Jake is an electrochemist, and he just started learning organic chemistry in my group since he joined about 1 year ago. So the idea here is to use model substrates like an aryl boron reagent, an alkyl boron or carboxylate, and a benzyl organoboron reagent. This way that if we oxidize these different types of intermediate, we would generate 3 different radical types, an aryl radical, an alkyl radical, and a benzyl radical. And then this radical will either undergo functionalization or homocoupling, indicating selective radical formation, or it could undergo grafting or over-oxidation to generate carbocation and a lot of oxidized products. So as you can see, the biggest question here would be, or there are so many mechanistic questions that you could raise, but probably the most interesting question would be, what is the effect of current that you apply or potential you apply? And the frequency of alternating polarity as well as the electrode potential with respect to the outcome of the reaction. And so here's just one example of what this mechanistic paper is all about. So we have here an alkyl boron reagent. So it would generate an alkyl radical. Homocoupling would generate this homocoupled product 7. And we run multiple reactions. So these are just 3 sets here. But we do run multiple reactions and generate a plot. So this is a plot that allows us to look at the correlation or relationship between current density, the frequency that you apply, the potential of the electrode, as well as what happens to the outcome of the reaction. So for example, for an alkyl radical generation, if the frequency is too fast, usually the potential would also be, and current density is low, the potential is low, and no reaction would happen. If current density and frequency is low for this particular reaction in here, over-oxidation or poor mass balance would be observed. But then you will start to see a sweet spot where just the right amount of current density frequency, you hit the right potential, and homocoupling would happen. So we were able to take advantage of this mechanistic information that allowed us actually to develop the right methodology. So because basically when you start this reaction, how do you know what frequency to use? How do you know what potential or current to apply? And there's just so many parameters that you can play around with. But this platform, or I would say potential map, has allowed us to, at least for the case of benzyl, because benzyl is something that's not represented in our substrate scope. Benzyl is also not represented in Barron's Colby electrolysis paper 3 years ago. But now we are now able to cross-couple benzyl effectively by using this potential mapping experiment. And so to summarize what we've learned mechanistically, if you apply a constant electrolysis reaction, you hit a certain potential until that potential is no longer controlled. So you're just going to be, let's say, for this case, oxidizing either the substrate, the intermediate, or the products. And so if our desired reaction is to oxidize an alkyl or aryl boron reagent, you would generate the desired aryl carbon-centered radical that undergoes a homocoupling reaction. Over-oxidation of the substrate would give you a lot of unwanted products. Over-oxidation of the radical intermediate would then lead to a lot of byproducts as well. Or over-oxidation of the product would lead to, again, a lot of undesired reactivities that we all observed in these reactions. But if you apply alternating polarity, it's some sort of controlling both the oxidation and reduction potentials. In this case, by finding the right frequency and current that you apply, you would be able to achieve just the right oxidation potentials to apply to the substrate and the reaction that you want. I'm going to end the first story there and start with the second one. So my postdoc, Eva, when she was trying to do aryl CH fluorination electrochemically, she actually ended up with a different product. So she was trying to convert this CH bond into an aryl fluoride using select fluor as the fluorinating reagent. But in this particular reaction, what she found is almost a quantitative formation of an aryl CN bond with an excellent selectivity to the para CH functionalization. When we started to look at this product, it turns out that Tobias Ritter has a similar reaction, but using a bimetallic catalysis reaction 10 years ago. So we decided to work on this for many reasons. Probably one is that we were really excited with the excellent site selectivity of this reaction, and of course, the importance of amines in pharmaceuticals and medicinal chemistry. And as we all know, aryl CN bonds, the formation of aryl CN bond is the second most used reaction in medicinal chemistry today. And the state of the art is to use palladium or nickel catalyzed Buchwald-Hartwig reaction, as well as SNAR reactions. So really wanted to work in this area where we could convert aromatic CH bond to an aryl CN bond. And there's been a lot of work in this area in the past 15 years. And the biggest challenge has always been selectivity and the scope, especially on the array. So to summarize what's been done in the last 15 years in the area of aryl CH amination, there seems to be two common mechanisms or approaches. The first approach is to oxidize an arene that is easy to oxidize to generate a radical cation and then trap it with an amine to form a CN bond. The other mechanism is to use an iminium ion that undergoes reduction to the N-radical cation, which is now electrophilic nitrogen source that reacts with a nucleophilic arene and generate an aryl CN bond. So this is the basis of, or this mechanistic manifold here is the basis of many amazing works by Yoshida, Rita Leonori, Nisevich, Sanford, and many others. And so we dig into this chemistry and the discovery of Ava that select fluor under electrochemical condition would generate an amination reaction. So we were really fascinated about the charge transfer as well as this radical cation pi interaction that was proposed in an enzyme by David Britt from UC Davis, where an N-radical cation intermediate could undergo interaction with an electron-rich pi system. And depending on how strong this interaction is, a charge transfer could happen. So there are different types of N-radicals that you could generate, at least for our case, electrochemically. So one would be a neutral N-centered radical, a monocationic N-radical, as well as a dicationic N-centered radical. And it's well known in the literature that a dicationic N-radical would be the most highly electrophilic of all these N-radicals. So we're really fascinated about utilizing this and generating it electrochemically. So Eva's discovery is that using select fluor, we could do one electron reduction and generate this dicationic N-radical as proposed in previous slides. And in the presence of an arene, we would propose this radical cation pi interaction, C-N bond formation would happen. And that is actually the proposed mechanism for this particular reaction. Probably one of the things that we really liked early on is how simple this reaction is. As you can see, an arene, select fluor, electricity, and just catalytic amount of triethylamine to do this reaction. We don't use any transition metal catalyst or a ligand in order to achieve this excellent selectivity. So we looked at the scope of this reaction, and it turns out to be highly functional group tolerant. So you can see that using fluorobenzene, we get almost quantitative yields. We could functionalize a lot of mono-substituted substrates. In many cases, we only get either one regioisomer. In some cases, it becomes challenging, for example, toluene, where you would get a fall off on the selectivity. You will also see that in many cases here, there are a lot of functional groups that we could tolerate, like nitros, a lot of N-heterocycles. Probably the most interesting ones are pyridines, bipyridines, and terpyridines. These are sometimes used as ligands in transition metal catalysis, and we could actually use them as substrate and achieve some sort of good yields and moderate selectivities. So we could also do a lot of late-stage functionalizations. These are from drugs that you could just purchase. You can easily convert the CH into the amine that you perform the CH amination. Probably the most interesting mechanistic information that we have for this particular work is that, well, our collaborator, Osvaldo Gutierrez, is that Fukui index is a good measure for the achieved regioselectivity. So Fukui index is a calculated value wherein the higher the Fukui index, the more susceptible that particular carbon center to be attacked by an N-radical cation. So for this particular case, for all at least the substrates that we've tried, the site selectivity where the Fukui index is highest, that's also the regioselectivity that we would observe under experimental conditions. So this would be a really great way to do in medicinal chemistry, because even you perform the reaction, you already know where the product or the CH amination would happen. So this is just a bigger picture of the mechanism. One electron reduction generates this dicationic N-radical. Trapping of the arene, you'll generate this, at least how we propose, an radical cation pi interaction, charge transfer, followed by C-N bond formation. Oxidation of that radical, sorry, there's a typo here. You'll get this carbocation. Elimination of the proton regenerates this aromatic system. Take note here that this DABCO could also undergo a competitive over-reduction and generate this DABCO if the arene is not a good substrate to react with. Okay, so while we were working in this area, we started to learn a long-standing challenge, a gap in this CH amination reaction. As I have mentioned earlier, there are two approaches. That is, either you oxidize the arene to the aryl radical cation. The fundamental limitation here is that it only works with highly electron-rich arenes, for example, anisols, naphthalenes. Toluene sometimes is actually a challenging substrate for this approach. The second mechanism, which is related to the mechanism that our chemistry is working on, is the reduction of an NX reagent to the N-radical cation. Under these conditions, one could only functionalize up to electron-neutral arenes. There are some reports where they would be able to functionalize electron-deficient arenes, but they are not selective at all. So at least before our work, there's been no general method of a selective CH amination reaction of highly electron-deficient arenes. And so we were quite curious about this, and we're really hoping that this highly electrophilic dicationic N radical is a solution to that problem. And so grad student Griffin, I think he was a first year during that time, he started to look into this on why our chemistry does not work with electron-deficient systems. So using benzonitrile and nitrobenzene as substrates, if we perform this reductive electrochemical CH amination reaction, we would always end up with recovered. Almost all of the arenes are recovered, but we always observe the over-reduced, the 2-electron-reduced select fluor, indicating that after one electron reduction, maybe we generate this radical cation interaction, but it's highly weakened if this arene system is electron deficient. And therefore, this N-radical cation would then competitively undergo a second reduction, and therefore leads to 2-electron-reduced select fluor rather than CN bond formation. And so a great strategy in order to avoid all of that is to develop an oxidative CH amination reaction, specifically oxidatively generating the N-radical cation from a DABCO, or a simple amine. So the mechanism would look like this, where you start with a DABCO. One electron oxidation generates the same intermediate, dicationic N-radical. And since this is under oxidative conditions, you would then expect that maybe this N-radical cation pi interaction is preserved and CN bond formation would happen. So this design looks so simple because it's just a switch from reduction to oxidation. But if we actually looked at the overall reaction, it's quite challenging. So there are actually two fundamental challenges that we already knew at the beginning. Most of oxidatively generated N-radical cations have only been shown only for HAT processes in either electrochemically or photochemically, and never been developed for arene CH amination. Second, we needed a proton reduction to couple this chemistry. And the source of a proton is usually, let's say, an organic acid. And this would then protonate your amine. And once your amine is protonated, they're no longer susceptible towards easy oxidation. And so Griffin started to look at this reaction. It keeps failing until the magic solvent or additive was actually HFIP. So HFIP as a co-solvent is also our proton source that undergoes proton reduction on the Cantor electrode. And HFIP is not acidic enough in order to protonate the DABCO as the amine source. So from here, we could now functionalize nitrobenzene and benzonitrile in modest to good yields and great regioselectivities. Just to demonstrate the scope of this oxidative CH amination reaction, we could functionalize pretty much a lot of electron-deficient systems. So we specifically looked at mono-substituted arenes because usually people would avoid using mono-substitution substrates because the fact that regioselectivity would become a problem. So as you can see, we do get modest, in some cases, only one regioisomer. If we compare it to our previous work, we either don't see any reaction at all. If reaction happens, either the yield is really low. We were also able to use this chemistry to functionalize a lot of pyridines. And as you can see, we have been functionalizing at the C2 positions, and only Chichi-Babin reaction would be the most general way of incorporating an amine at the C2 position of a CH pyridine. So there are very few methods to do that, but we could do this using this reaction. Another advantage of this oxidative approach is that we are no longer limited to select fluor as the aminating reagent. In principle, you could just take DABCO, do a simple N-functionalization. So we can now put in a lot of even interesting and sensitive functional groups. Now we use this dubconium as nitrogen sources and perform this electrochemistry. So this reaction will then lead us to a lot of derivatives of aryl dubconium salts with different R groups. And we've been applying a lot of ring opening reactions, so we could actually open this aryl dubconium salt and generate these aryl piperazines. And aryl piperazines are highly frequently found in FDA-approved drugs. And we could now liberate these aryl piperazines together with these pendant functional groups that we have installed at the beginning of the generation of this designer dubconium salts. So one of the most frequently asked question that I always get is that, are there reactions that we could develop for aryl dubconium salts? So imagine performing a reductive or oxidative CH functionalization to generate aryl dubconium salt. We have demonstrated that we could generate a various type of aryl piperazines via ring opening reactions, but this aryl dubconiums has reduction potentials that are actually somewhat in between aryl bromides and aryl chlorides. And so if you are going to just look at the literature and find reactions that functionalizes aryl bromides or chlorides via one electron reduction process, we could actually adopt them with just very minimal optimization on those conditions. We could do a CH amination followed by photocatalytic CP bond formation, CC bond formation, and carbon-boron bond installation. We could isolate the aryl dubconium salts, which I think it's good for medchem. Here's one example of a crystal structure. Or we could just do an in situ operation and generate the desired product from here. So before I end, I just really wanted to summarize what I have so far with electrochemical CH amination. We were able to develop an electrochemical approach that generates N-radical cation intermediates reductively or oxidatively, and do CH amination to generate aryl dubconium salts. With respect to the amine source, we could do quinoclidine as the nitrogen source. So that's not a big improvement, but I'm going to share with you later what we have done from here. So we could do an aryl quinoclidination. We are finishing up this work. We could also trap N-radical cation with an olefin and generate an alkenyl dubconium product. As you can see, to me, this is a really unique reactivity because we are not touching the alkene. We're actually, instead of a hydroamination, we're actually doing a CH amination reaction here, which to me, it's quite a rare reaction. But the most interesting reaction that we had, at least for about a year now, is that could we take advantage of this platform in order to discover an sp3nn bond formation reaction? And the strategy would be to oxidize or reduce and generate N-radical cation and then trap it with an amide and form an sp3nn bond. So I guess for the grad students and the postdocs, I think they're very much aware with what's in the literature. And there are a lot of methods to make NN bonds, but all of these methods, either both nitrogen or one of the nitrogens, is sp2 hybridized. There's no general methodology out there that allows us to construct, for example, an sp3nn bond, as you can see in piperazic acid or fabulin. Most of the NN bonds that you would generate in any other way would be an sp2 NN bond formation. So here are just some examples of FDA-approved drugs or natural products that contain NN bonds that we can find. And I think a fact here is that despite the presence of nitrogen in a lot of FDA-approved drugs and natural products, there's only about 300 natural products that contain an NN bond out of, I guess, about 400,000 natural products out there. So this is less than 0.01% representation of NN bond. And this is not actually surprising because chemically, it's not easy to make. And second, even nature struggles to make an sp3nn bond. My favorite in this list is actually fabulin. As you can see, this is a very unique structure. It contains a piperidine core that is dimerized at the NN bond. And probably, I think, with my experience as an organic chemist, I don't often see a structure that looks like this. So as I've mentioned earlier, making an sp3nn bond is difficult. even so for an SP2, SP3. So we actually looked at everything in the literature. So there was this paper that was published more than a year ago, where they were able to report and say that they were able to found a condition oxidatively that you could make an sp2, sp3 NN bond. Unfortunately, this paper was retracted a few months after its publication because it's then reported that all the structures they reported are actually wrong. But indeed, what they observed is this rearranged product, and there's just no NN bond that's formed. Nature also struggles to make sp3 NN bonds. In fact, the first report of an enzyme capable of making an sp3 NN bond for the case of piperacid acid was just reported last year. This particular enzyme is capable of oxidizing this amine, generates a radical, and forms this sp3 NN bond. And so going back to our strategy, could we develop an electrochemical sp3 NN bond formation? So the idea is to electrochemically generate an radical cation and then trap that with an appropriate amine, and you would get an intermediate that looks like this. So for the grad students and postdocs out there, you might be wondering, this has to be an unusual intermediate because it's a hypervalent nitrogen. So as you can see, this is a two-centered 3-electron NN bond. It is quite represented in the literature, but it's usually not adopted in organic synthesis as an intermediate. So while this might be a difficult intermediate to generate, there's actually a report, actually 2 reports in the literature that's giving us a hint that it's possible to have this intermediate and maybe use it for organic reactions. So one report is, these were actually 40 years ago, is the use of this diamine as the nitrogen source. 1 electron oxidation, they were able to observe this 3-electron sigma NN bond observed by EPR, and further oxidation of that, they were able to isolate this dicationic NN dimer, which to us, it's basically telling us that it's possible to form an sp3 NN bond. And so using that knowledge and the things that we've learned in our research group, we started to really evaluate this reaction carefully. Grad student Griffin and postdoc Sang-Yuan Lee has really focused on their time in making this to work. And so here's just an example of an electrochemical oxidation of quinoline through time. So this is basically the charge passed through time. And we monitor the NMR. As you can see, we would start to see the formation of a pink as the final product. And we were able to isolate that product, and it's indeed an sp3 NN bond formed wherein one of the quinacridine is opened by an acetate. And this acetate is mainly coming from the acetic acid as our sacrificial acid. But then there's also this intermediate that's growing, and then it goes down as the reaction progresses. We were able to characterize and found that this is indeed a quinacridine dimer. And as you can see, it's again an indication of an sp3 NN bond formation. So from here, we were able to optimize 2 strategies. One is in the presence of acetic acid, where you're going to end up with this sp3 NN bond. 1 quinacridine is opened up, and then the other one is intact. Or another methodology is to remove acetic acid and redevelop that in order to end up with a quinacridine dimer. So we can now take advantage of both strategies in order for us to make a lot of derivatives of flavulins. So here would be utilizing strategy 1, where you end up with this intermediate, and then you treat it with a nucleophile. As you can see here, just some of the nucleophiles that we could use: a carbon-based, a nitrogen-based, a sulfur-based, an oxygen-based nucleophile, and generate a lot of novel fabulin derivatives. Another way is to utilize the strategy where you end up with a dicationic or the dimer quinacridine. You open it with the first nucleophile, you generate this intermediate. Here are just some of the examples that we could do. This is highly electrophilic, so there's actually a lot of nucleophiles that falls into this category very well. So many of these are nitrogen-containing nucleophiles, sulfur, oxygen. So from there, we could treat it with a telescoping with a second nucleophile to generate novel fabulin derivatives. And similarly to the first strategy, we could incorporate carbon, nitrogen, sulfur, and oxygens. I'm going to end there. I think this is my summary slide. I hope that I was able to convince all of you that starting with a simple question, digging into fundamental understanding utilizing that knowledge in order to elevate the chemistry, we could use electrochemistry not only to develop a reaction, but also discover new reactions that are impossible in any other ways. As you can see, from organoboron chemistry to the cross-coupling of an acid and boronic acid. In the second example, from our CH amination project to an electrochemical process of making sp3 bonds. I want to thank my group again, and again, thanks to the organizers for having me, and I could take any questions from here. Thank you so much.
Thank you, Christian. I am seeing a question in the Q&A, and I would like to encourage you to maybe write in your responses that you want. That there might be more questions that come up too as we transition, and we're going to do that immediately in lieu of time. I will turn the floor over to Alex, who will introduce our next speaker.
Thank you.
Thanks, Alex.
Thank you, Christian.
Great talk, Christian.
Thank you so much.
So our next speaker of the day is Kate Harper. So Kate, oh, he's already started sharing. So it's really a privilege to introduce Kate Harper, who is a principal research scientist at AbbVie. Prior to joining AbbVie in 2015, Kate obtained his PhD at the University of Utah in the laboratory of Professor Matt Sigmund, where he worked on developing multi-dimensional free energy relationships to guide asymmetric catalysis. This was followed by a postdoc with Professor Eric Jacobson at Harvard, where he developed new hydrogen bonding organocatalysts for stereoselective glycosylation reactions. Today, Cade leads a group within process chemistry known as the Innovative Chemical Technologies Group, which consists of chemists with specialties in areas such as data science, electrochemistry, flow, among others. The goal of this group is to develop technological proof of concepts so that when a pipeline need arises, a solution is already available. One area of current development is electrochemistry, which will be the subject of today's talk. We look forward to your talk, Cade, and you can take it away.
Thanks, Alex. Just a quick sound and slide check. Everything look okay?
Perfect.
Thank you. And thank you for the kind words. It's an exciting opportunity for me to be able to share some of what we're doing here at AbbVie in terms of electrochemistry with this audience. So with that, Alex also did a great job in introducing my colleagues here, the Innovative Chemical Technologies team. It's a privilege to interact with all these individuals on a daily basis. And I'm in a unique circumstance where I know that I'm at a highlight of my career, and I can acknowledge that and enjoy it without having to look retrospectively back at it. I know that I'm in one of the best jobs. I love this job in this group. So we have a unique mix of different technical expertise and a lot of creativity, and we try to address forthcoming problems or things that we identify that we want to scale or have a path forward to scale proactively. And one of those has been electrochemistry. And we've been active in electrochemistry, I would say, for at least 10 years, the full time that I've been here, more active maybe in the last 8. And so I'm going to provide some perspective about our journey through, and then maybe even some future looking perspective if there's time for it at the end. But to get started, why are we interested in electrochemistry to begin with? Well, I think some of this is self-evident, right? So you look at the principles of green chemistry, electrochemistry is well aligned with many of these principles. And as a process chemist, we want to bring forward the greenest process possible, the friendliest process. So electrochemistry fits into that paradigm very well. But I actually get more excited about another component of electrochemistry, which is its selectivity. So if you think about the canonical reagents for redox manipulations, so both reduction and oxidation, I think I looked it up in the organic chemistry portal. There was more than 200 oxidation reagents listed. And across those, you have, a full scope of different potentials that you could access, and oxygen transfer reagents and all types of reagents. But what it really requires is kind of a canonical knowledge and an encyclopedic knowledge of those reagents, where to apply them, And beyond that, they're still discrete variables. Where electrochemistry, in terms of oxidation and reduction potential, gives you allows that to be a continuous variable. You can tune it in. You have a dial now that you can tune into the chemistry needs of a specific substrate. It doesn't eliminate some of the completing or some of the confounding effects that you might see within that. And we'll get into that as I tell some of these stories that we've accumulated over the years. But I really get excited about the ability to tune in to a specific potential and then execute oxidation or reduction based off of that. So now some perspective. 8 years we've been playing in this field pretty actively. And when we first got started, we had some serious questions about how are we going to develop a workflow for electrochemistry. So reaction ideas, they're going to come from the literature. We've all noticed the uptick in the number of different methodologies. Particularly, I mean, Christian showed us 2 very powerful ones today, right? So the ideas are coming. So then what do we do in terms of reaction discovery? How do we evaluate the reactions that we're interested in at a very kind of minimal level, requiring minimal amounts of material? Can we fit them into our HT workflows for questions? Once we identify reaction lead candidates, if you will, something that we're interested in or that there's a value statement behind, how do we optimize that? What variables are we looking for to optimize against? How do we scale it? And then how do we launch this into commercial products? These were all questions at the beginning 8 years ago. And this kind of coupled against what I like to call the discovery process time continuum, which early on in discovery, you have an open synthesis. And as you progress through development of pharmaceuticals, the ability to change parts of that synthesis become increasingly challenging. Now, I don't want to portray that there's no chance that you can change a synthesis even at the end or past commercial launch. We can and we have, but it just becomes more and more challenging. The proposition or the value proposition that you have to develop becomes more and more intense to change this kind of synthetic momentum that builds through the development process. The questions beyond some of the questions you have to answer go beyond it's just a better reaction or it gives a better yield. You have to address things like impurity profiles. So as we go along this, I'll highlight, right, in early discovery, synthesis is open by and large, and you can execute. Now, as you start to scale into the tens and hundreds of grams, we have windows of opportunity to then change the synthesis or implement something new. But those windows open and close in relatively short timeframes, maybe a couple of months is what we'll get. And then once we get into human trials, we might get a little bit wider windows in between those trials as they come and go. But again, it's a defined window where depending on the project, the importance, et cetera, we can divert resources to development in some cases. So these are the windows that we want to operate against and the value statements that we need to create to implement these syntheses. And part of the way that our group thinks is we need to have a lot of the fundamental questions answered before we can provide these kind of statements, before we can look to a team leader and say, yes, we can implement this and in this amount of time and with these partners or with this, and lay out the path forward for them so they're more comfortable making the change. So getting to how we discover these reactions. I'm not going to talk a lot about this. I'll reference some of the work that's been done externally. So Song Lin and Merck kind of launched into this field with the first look maybe at high throughput electrochemistry and leveraging equipment that we're all very familiar with in the HT world. Song built on that with his collaboration with Olwix, where they developed specs. We made our own modification building off of some of the work that they put out there, where we leveraged 4 channels or let's see, 6 independent 4-channel not potentiostats, but power supplies to help drive each well of a 24-well array individually rather than in series. And I wanted to highlight, and Corinna gave me permission to highlight something that her group is working on, which I'm really excited about getting implementation on, which is a more comprehensive look at how to screen reactions. So they're looking at a 40-well array, and they've, again, printed custom PCBs and leveraged battery cyclers where they've kind of had to hijack the software and the capabilities of these battery cyclers, but can do now 40 individual well control. And not only that, but they've leveraged computer vision and some high-level algorithms to extract out not only CV data, but bulk electrolysis data, and are really creating a full package workflow for how to develop an electrochemical reaction from, idea conception all the way to kind of implementation. And then where we would want to then take is pick that up and say, okay, this works great in a well, but how do we then scale that further? So I'll address that with kind of what I'm going to talk about today. But I'm also very excited about the ability to do high throughput CV with some of the innovation that they've come up with, including a reference electrode that's easily miniaturizable and seems to be pretty robust. So I don't want to tease out too much, but look forward to hearing from that group some really exciting discoveries that they've made and some results that they've generated. So we've kind of answered some of the questions about what the small scale and the HTE world can look forward to in terms of electrochemistry. But then what? How do we take and translate results from that HT screen into reaction optimization in preparation for scale up? What are the parameters and what do we need to be thinking about? So, a lot of this optimization and scale up go hand in hand. So I'm going to try to broach both of these at the same time. And you say, well, scale up's known in electrochemistry, right? So there's many chemical processes that are done in the fine chemical industry on massive ton scale. So this is a solved problem, right? I would argue that it's not for the pharmaceutical space. So obviously things like the chloralkali process, the adiponitrile process that are very well established are built with bespoke chemical reactors that really aren't modular, flexible, agile, put in your word there, but they're really based off of the ability to look at the end game market and say, this chemical is worth X dollars per gram or per ton. And now can we devise a process that fits that? And the pharmaceutical world doesn't operate in that regime, right? So what we need is speed, flexibility. Like I said, we're trying to operate within those windows of opportunity to implement new syntheses and new techniques. So we need something that's more flexible, right? We can't devote a lot of resources and money to developing reactors like this that might get used maybe once every couple of years, right? That doesn't make sense. So we're trying to fit into this space here that I've defined as the pharmaceutical space, where it's more on the kg per day throughput needs that, but we want rapid deployment over highly optimized processes where other reactors are driven by economics. Ours are going to be driven by the advantages in selectivity and reactivity that I've already highlighted. So that led to kind of a simple thought experiment, which is, if we put some kind of standard parameters on this, let's just assume 100% Faraday efficiency. I know nothing's going to be that, but let's just, for sake of argument, assume 100% Faraday efficiency in a given reaction for a molecule of median molecular weight. How much amperage do we need to drive a 2-electron reduction or oxidation? Well, if we want 1 kilo per day throughput in any given flow setup or something like that, we're talking about 6 amps. Of course, if it's 4 electrons, it's 12 amps. And if it's 6, it's 18, right? That's nice and linear. If we jump that up to 10 kilos per day throughput, that might facilitate, say, like a phase 1 or a phase 2 study. We times that by 10, 60 amps, 120 amps, 180 amps, right? Now we're starting to get to some concerning levels of amperage, stuff that's going to make plant engineers uncomfortable. And then you jump that again to 50 kilos a day, which might facilitate a phase 3 study or even a commercial launch, depending on the program, the target, the dose, et cetera, right? Then you're talking about 300 amps, 600 amps, 900 amps. That's a lot of current that you're going to have to build into infrastructure, right? And have some really interesting discussions about safety. But with all of that, right, the caveat is this is going to be relatively low voltage current, so we can do it. We shouldn't be too hesitant about that. We just need to think about it and implement it carefully. This thought experiment got us thinking, okay, how do we hit these different levels and do that in a way that we can do it rapidly? And we looked with my colleague Matt Graff and with the Stahl group. This was kind of where we dove into our first scale up, I would say. So we used what was out there, which is these parallel plate reactors that are very well established in the field. And we just looked at doing an oxidation reaction that the Stahl group had developed. And what we found is that we could execute this, right? We did this in a recirculated flow manner. We had to do some on-the-fly pH adjustment to maintain the EE levels and the other reaction outcome components that we wanted to maintain. But we could do this, but we saw a lot of potential flaws in that, results from the small scale did not translate directly to the large scale. It essentially necessitated a re-optimization of reaction conditions, which is not ideal from a rapid scale-up perspective, right? And also we learned that while recirculated flow is something that we can do, oftentimes single pass flow will be more ideal or allow for higher throughput overall and save us that time that we're so desperate to save. So then another thought experiment, right? So if we go to pretty standard conditions that we see published in the literature using the icoelectrosyn or any number of homemade apparatus, right? If we're running at a pretty nominal current and a pretty nominal amount of this electrode submerged in the reaction solution, you get typically maybe like this current density. And if you translate then and you couple that to that other thought experiment that I just put in front of you, which, for this many kilos, you need this many amps, what you get to is to achieve roughly a kilo a day, you're going to need 11 amps. You're going to need this much surface area, roughly the size of a closet door of electrode surface area to scale that appropriately. Similarly, if you want to go to 50 kilos a day, you're going to need the surface area of a racquetball court to facilitate that. That's a lot of equipment. That's a lot of consideration that needs to go into building such a large reactor. Again, that's going to be a problem for us for that rapid scale up. So this is thoughts that Jeremy Griffin put together in collaboration. And we said, well, is there something that we can do? Oh, I'm getting ahead of myself. Let me also highlight, I don't want to rail too much. Those of you that know me or interacted with me know that I'm not a big fan of these parallel plate reactors. I don't want to bias too much, but I can say from a flow chemist perspective, which is how I came to this problem, right? I had more experience with flow chemistry, very little experience with electrochemistry. The flow patterning in a parallel plate reactor as typically designed and implemented is poor, right? So you have a lot of flow coming in through the inlet and it rapidly goes out the outlet and kind of channels the flow where you get these back eddies that are poorly mixed with excellent mixing along the flow channel. And you can model this, and we have and looked at that kind of extensively and said, yeah, there's areas here where their current density should be excellent, but also areas where the current density is not going to scale linearly. And that's all just based off of the fact that we're coupling our mixing with our flow. So I highlight, there's some solutions that the parallel plate field has put out there, turbulence promoters. They've, created channels, but some of these compromise some of the advantages of these parallel plate reactors, which is, you start to lose surface area. I just highlighted surface area is going to be important. Similarly, you can do a divided cell in a parallel plate, and none of the other reactors that I'm going to talk to you about today have that capability. But again, you have poor circulation, you have mechanical challenges, and essentially it necessitates, to get to the proper surface area, recirculation and flow. So our approach to this was to say, can we design a better reactor? Can we improve on what's out there already? Can we balance surface area to volume? Can we make this modular so that we can rapidly implement it against a variety of different electrode materials and take some of these other considerations that we found in evaluating parallel plate reactors like gas liquid fouling, et cetera, and try to solve some of these in one fell go? And the way that we approached this was using the principles of flow chemistry, which I was more familiar with. Most of the flow reactors that were out there, the parallel plates, kind of lean on the principles of plug flow chemistry. Now, I would say none of them are great plug flow reactors, but the ideas behind them are based in plug flow. And what we said is for these reactions, for electrochemical reactions, generally speaking, they're going to be driven by mass transport phenomena, which means that they're concentration independent, usually of the elements. So if you're thinking about starting material, right, it's a linear decay, a straight line decay of that starting material down to zero, and that's just based off of the applied current or voltage. So based off of that, we said, could we apply a continuous stirred tank reactor, which the only negative, right? So both of these are good flow reactors, and both of them have their application. But in cases where there is essentially zero order kinetics observed, distinguishing one of these reactors from the other becomes kind of a moot point. There's not really an advantage or a disadvantage to either one in terms of throughput, but what there is an advantage for in a continuous stirred tank is you can decouple the mixing from the flow rate. So we said we have the ability within a CSTR to rapidly stir and enhance mass transport through stirring and good mixing that we don't have in a parallel plate reactor, where the only way we have to enhance mixing is to turn up the flow rate. So with that as a principle, we designed a set of flow reactors. I have one here. I can put it up in front of the camera. You can look at the pictures, right? So this is now a series of rods arrayed in a circular pattern, and then they alternate between anode and cathode in the way that they're wired. And really, I want to give credit because you notice in these pictures, these are all hand wired, right? So this was one of the initial downfalls, right? As we started to implement this and see some of the positive impact that it could have, it necessitated me or Matt or Jeremy or Simon or anybody else that was playing with these reactors in the early days to go through and electrical tape, hand wire these. And we used to get, kind of teased by our colleagues. It looked like we were making bombs. And we wanted to avoid that. Really, the innovation came out of the Stahl group up at the University of Wisconsin and Matt Johnson, who developed this kind of a custom printed circuit board that he could couple with these battery clips that provide nice contact, which was something that we really struggled with early on. And very modular, we can slide these in and off the reactors. It really makes them much, much easier to use. So now with that innovation from Matt, we can have a lot cleaner look, a much easier to operate look or reactor. But we're balancing, again, surface area and volume. We can do this across scales. We're modular, so almost everything is available in a 1/4-inch rod. Any material that you could choose, you can get in a 1/4-inch rod. So here, graphite, copper, stainless steel, the most common electrode materials, but even fancier electrode materials, cobalt, manganese, I have silver, all possible to obtain in 1/4-inch rods. So it's nice we can get these diverse materials, plug them in. Of course, CSTRs, because they are well mixed and decoupled mixing from flow rate, you have solids compatibility, so you have some precipitate, some fouling. It's not going to be the end of the world. Gas liquid compatibility, obviously, so the gas can evolve out of the reactor independent of the flow pattern, which is nice. And then we thought this might set us up for success in single pass flow chemistry. So we built these on 100 mil scale. These are built to model automated lab reactors that we have access to. So these couple nicely with our EasyMax reactors. You can use them independent of the EasyMax, but the EasyMax is a really nice way to implement temperature control, which as a process chemist is bread and butter. We need to demonstrate or have control over the temperature of any reaction we run. We can do this at 100 mil scale, which is this reactor on the left, 400 mil scale. And then this required a custom piece of glassware being built from ChemGlass, but about essentially an 8-liter CSTR, 7-liter CSTR could be built because the total volume of the 96 electrodes that are present is about 1 liter. And then we wanted to then demonstrate the scale-up parameters. And we said, okay, what's the most challenging system we could think about in electrochemistry? And Jeremy identified, let's do constant potential and single pass. So that's what I'm going to talk about as a story and the system that Jeremy Griffin developed to attack constant potential single pass flow electrochemistry. If you think about the 2 different modes that you can run electrochemical reaction in, right? Christian highlighted these in his talk. You can run at a constant current, which over time your potential should rise. There's ways to defeat this, right? And people have been very clever about how to implement this, but in a general electrolysis reaction, this is what you would observe. And then in terms of if you're looking at an analyte of interest, you'll see that concentration of that analyte of interest will go up in a 0-order fashion, right? Just based off of the applied current. But over time, as that potential rises, you might start to sacrifice some of the product that you've made to overoxidation or overreduction. And that will be challenging independent of flow path. Now, the other approach that you can take is you can say, all right, I'm going to lock in my potential, and then you'll have a current regime that eventually will fall off over time. And if you look at that in terms of the analyte of interest, concentration will increase, but you'll kind of more approximate concentration dependence on this reaction. So you're going to get lower rates overall and lower currents. So we said, can we defeat this effect where now, you know, the throughput effect of this is going to be magnified in flow. So the reaction that Jeremy identified was a Shono oxidation, right? This is a reaction that's very interesting to the pharmaceutical world, right? The ability to implement something oxidatively to alpha to a nitrogen where there's so many heterocycles present in the molecules that we make. Pretty simple conditions. Jeremy optimized these to minimize the amount of elimination byproduct, so this alkene, as well as overoxidation. And he studied this overoxidation, right? This was actually part of the design. We wanted to have this challenge of an overoxidative or an over-reduced byproduct being formed. And in the CV, you can see, yeah, clearly there's the first oxidation, and then the second wave comes in with the overoxidation, and he even validated that against the product independently with this a CV of its own. And he devised the oxidation potentials. So the gap between these is about 0.3 volts. That's the resolution that we want to tune in, where we want to achieve monooxidation of this starting material selectively and minimize the amount of overoxidation, right? Because as a process chemist, any byproducts that we make, we have to get rid of, and that can complicate how to implement a process. So again, the electrolyte is optimized to minimize the amount of elimination byproduct, as well as the temperature. We saw a direct effect on the amount of elimination. So Jeremy started studying this reaction. It's a well-behaved reaction. You see product again forms linearly, but then you start to see the concentration of the product fall off as it's consumed in the overoxidation pathway. He studied this in terms of mass transport, so looking at different applied potentials. So these are just cell potentials. He saw, of course, corresponding initial rates. As you go to the higher potential, you get a very fast rate, and eventually you can saturate that at about 6 volts. That's the fastest rate that you're going to achieve for this chemistry in a well-mixed system of this type, right, with the reactors that we're using. You start to back that potential off, you see a corresponding decrease in rate. Similarly, right, just verifying that this is largely dictated, these rates that we're observing are largely dictated by mass transport. You know, in poorly mixed systems, we see lower and lower levels, and we, in the upper right corner here, we've evaluated the mixing profiles of these reactions against multiple different impeller configurations, right? So that's something that we studied early on, and we see, yeah, with the additional stirring elements against an impeller, we can get really excellent mass transport in these reactor systems and drive the reactions to the maximum potential rate that we can. And of course, in an application of flow chemistry, rate is time, time is money. So let's zoom in here a little bit on this effect, because it led to an analysis that I called the Griffin analysis, which I think was really an excellent demonstration of Jeremy's creativity and understanding of the two fields of melding both electrochemistry and flow chemistry to create a reactor system that can be highly efficient in terms of space-time yield and selective. So yeah, here's the results at 6 volts. And you can see independent rates here. So these are independent reactions where he's measuring both this reaction here in red, as well as the reaction of the oxidation product to the overoxidated product. And you can see at 6 volts, you have a measurable rate of each. Obviously, the initial oxidation is a little faster, but as you back that potential down, you start to get to that sweet spot in the reaction where the rate is as high as it can be while minimizing the low rate or the rate of the overoxidation. But rather than operate in that window, which he could have said, listen, we're going to lock in at, say, 4.0 volts. That's going to be essentially no rate for overoxidation, but we're going to have this diminished rate of product formation and design a reaction system around that principle. Jeremy said, I want access to this fast rate, right? I want the 6 volt cell potential rate. I want that space-time yield, but I don't want the overoxidation. So here's how he paired those two ideas together. So he said, I'm going to divvy this up into 4 separate CSTRs. And of course, at steady state, your potential and your amperage, your current are going to be the same, right, at a steady state. So we're going to analyze this in terms of potential, but this is also a current, applied current as well. So in CSTR1, we're going to apply 4 volts of potential, and we're going to get this kinetic profile, right? This is our rate. Also in CSTR2, we'll apply the same potential, and we'll drive the reaction now to about 80% conversion. Then we'll push the materials over into CSTR3, where we'll have an applied voltage of 4 volts, and that will drive the reaction up in the amount of time that it is in CSTR3 up to about 90% conversion. And then in CSTR4, right, we'll get that last little bit of conversion out at 3.5 volts, where in CSTR3 and CSTR4, right, the rate of overoxidation is significantly diminished. So in designing a reaction system like this, we should be able to expect low levels of that overoxidation. And this is just another portrayal of that same reaction train, right? So we're going to say 22 minutes, 10 amps, 6 volts in a 400 mil reactor, 15 degrees C, and we get 36% conversion. We transfer it over to the next reactor, and we get an identical amount of conversion with the identical applied conditions. Then we bump it over to the third reactor. Again, now we're talking 5 amps, 4 volts, and we can drive the reaction up to approximately 90% conversion. And we push it over to the final reactor, again, all at the same volume, but we're toning down the applied potentials across all of these with the same resonance time, and we can expect 99% conversion. So Jeremy built this reactor train, and here's a picture of it. So again, coming in from the feed on the left through the pumping manifold and into CSTR1 that has an applied potential. You can see the power supply here off to the left, 10 amps, 6 volts, and reactor 1, reactor 2, 10 amps, 6 volts. So those are the first 2 reactors. This is the pump that's used to convey the materials between reactors, right? And this pump is just set with an outlet at a fixed height and just pumping as fast as it can, essentially. And then we go from CSTR 3, 4, hopefully coming out the product, we get our expected output. Now, in the spirit of being real, right, this experiment went well in that Jeremy was able to achieve largely what he was trying to achieve. Kilogram per day throughput, excellent yield, control of the impurities, both in the overoxidation. But one of the challenges that came out that we hadn't anticipated was there's quite a bit of ohmic heating at 10 amps and 6 volts, and it overwhelmed the capacity of this EasyMax, putting them together. So had he constructed this with CSTR1 and 1 EasyMax and CSTR2 and in the other EasyMax, we probably would have been fine. But he didn't do that, and we learned along the way that, so this is the real data. You can see that as the temperature started to climb, the reaction started to get out of control. Jeremy intervened with the help of Simon and Weld to try to get that temperature back under control, was able to achieve that to some extent. But again, it wasn't a perfect result, but we learned something from it where we knew, okay, this ohmic heating, we got to try to understand and better accommodate in any future scale-ups. And then again, he was able to execute this on scale with our large reactor system. Again, this is just a batch result, but we could take this batch result, say if we translated this into 4 reactors, same as the 400 mil scale that Jeremy had already executed the flow run on, we could expect roughly 27 kilos a day of throughput at constant potential. But in batch, this was a 700 gram reaction. It was approximately 6-hour reaction time total. And one of the key elements here is, right, we're doing proton reduction on the back end. And as a safety consideration, we had to aggressively sparge in nitrogen to dilute the hydrogen gas that we were forming in copious, dangerous amounts, really. So we diluted that down to a safe level of hydrogen in nitrogen. All right, I'm running a little low on time, so I'll gloss through these results that we've gathered with our collaborators at Minachem, so Clement, Pierre-Georges, PG, in this pinnacle dimerization reaction that they developed. And they came to us with these results, right? Saying, look, we've done this in recirc mode. We see that, with this, even as high as much recirculation, as fast recirculation as we can go, we still see a fair amount of this over-reduced byproduct that we don't want in our reactions. And they knew we were developing a new reactor type. And so they evaluated, again, say, similar current density, even based off of the rod, which, is an inhomogeneous electric field. But still taking this as a one-to-one, they saw they could minimize that. And this is primarily, we believe, due to the enhanced mass transport and decoupling the mixing from the flow rate. And then what Clement did is, I think this was a great lesson in ingenuity. I had supplied him with just a single one of these reactors. He went ahead and he simulated what it would look like to do a 3-stage CSTR design, where in stage 1, he applied 15 milliamps per square centimeter of current density. He passed that through the system one time, collected it, and then passed it back through, now at 10 amps or 10 milliamps per square centimeter, back through at the same resonance time, collected it all, and then passed it through a third time at an even lower current density to, again, achieve the same kind of result where you see the over reduction creeps up, but it's within that controlled level, that expected level, which is where we want to be from a process perspective, right? We can handle certain levels of impurities. Oftentimes we know what levels they are, and we can design systems now that can control to that level, which makes this much more easily applied in the process space. So that isn't to say that this reactor design isn't without some challenges, right? One of the things that we recognized as we built these reactors is we had to change from alternating electrodes to a pretty different electric field. And we saw the effects in the work that Jeremy done. We saw the effects in some of the applications that came through the pipeline. Yes, electrochemistry is impacting our pipeline. And we wanted to better understand and better be able to predict what these changes in electric field lead to. And that's where Jane joined, and she's a trained electrochemical engineer. She was able to supply us with some of the electroanalytical techniques that we needed. Specifically the ability to do impedance spectroscopy and then backwards extract out what we needed. So we could do the impedance spectroscopy, generate this Nyquist plot, pull out this RU value, and then solve this equation both forwards and backwards, depending on the scale and the translation that we wanted to make. So here from the ICA electrosyn, we can solve to get our V surface. We can plug that back in to the larger scale reactor and solve the equation for V power supply. And when we do that, then we can obviously take that result and apply it to our even larger reactor and use this impedance spectroscopy. The other element that we're really excited about, and Jane's going to pioneer on, is our ability to do wholesale CV in collaboration with the Stahl group in the effort to try to put out a formalized workflow for all of this. So again, we've talked through kind of this whole electrochemical workflow up to this rapid scale up that we want. And what I envision ultimately is once we achieve rapid scale up and we've implemented electrochemistry in the synthetic sequence, when it comes time to launch commercially, we'll be able to do so with a little bit more autonomy in terms of design, where we could then change to more optimal design. I'll skip this bit on alternating current and just thank all the people who over time have contributed to the electrochemical project. It's been a fun ride. And of course, with the few minutes that are left, I take whatever questions we have.
Thanks so much, Cade, for a really amazing talk. I'm glad that you could, share the actual reactors or pieces of reactor on screen. So thanks so much for doing that. Like Cade said, we have maybe 1 minute for 1 or 2 questions. So we'll see if there are any in the chat. Maybe in the meantime, basic question, but what's the biggest scale you've been able to achieve with electrochemistry?
In flow, that still is probably our largest scale up in-house that I highlighted. In batch, we've done everything. Sometimes it's easier to get that implementation done in batch to supply earlier phase or earlier deliveries. 300, 700 grams. It just depends on the reaction conditions. I will also say, we have a lot of these reactor designs. We're glad to share them with anybody who might be interested in them. So please just reach out if you're interested. I can supply the equipment.
Amazing. Thank you, Cade. I guess we're at time. So, please follow up with Cade if you have any questions you didn't ask, or perhaps if you want to borrow a reactor. But as we come to a close, we just want to thank our sponsors and affiliates, the ACS, Emory University, Beyond CCHF, as well as Alan Bailey for helping us host today's meeting, Scott and Steve, Hugh, my co-host Alex, and importantly, our speakers today, Cade and Christian, for really giving us a great look into different sides of electrochemistry. So until next time, have a great day, everyone.
Bye, everybody.
Thank you, Alex and Alex.
Thank
Alex,
you.
you crushed
Thanks,
it today.
Cade.
Yeah, thanks for the great talks, everybody.
Yeah, thanks so much for agreeing to be part of this. We really appreciate it.
Nice job, everybody. Good job, hosts. Good job, hosts.
We've gotten some yeses for the upcoming seminars. I think we're waiting to hear back from a few people still,
Cool.
but it's all coming together.
It's always nice when you have looking at the last minute.
Mm-hmm.
All right.
Well,
I've got to go run a column. So I will see y'all later.
good luck with that.